Erdős defined the foundational era of combinatorics by treating networks as abstract, dimensionless points connected by binary probabilistic links. While this abstraction revolutionized finite sets, it introduced severe conceptual friction as networks scaled toward infinity. Mathematicians found themselves unable to pinpoint the exact thresholds where these massive structures actually begin to emerge. The most prominent victim of this probabilistic approach was the diagonal Ramsey number. The upper bound, the limit predicting the inevitable appearance of a monochromatic clique, remained stagnant at a constant of 4.0 for nearly 90 years. This chart tracks the evolution of the Ramsey constant. Following a 90-year flatline, the 2023 breakthroughs by Campos and Gupta suddenly dragged the constant downward toward 3.8. They utilized a book algorithm using density boosts to force crystallization more efficiently. The Erdős-Rényi phase transition presents a second mystery. This curve identifies the threshold where isolated clusters suddenly transform once the average vertex degree reaches 1. Inside this critical window, components scale at a transitional phase that classical models cannot fully explain. While we have mapped the presence of these sudden structural changes, the underlying mechanical reasons for these transitions have remained hidden. The infinite fractal descent framework proposes that complete graphs are not theoretical abstractions, but physical systems embedded within a high-dimensional continuous spatial manifold. In this framework, the emergence of absolute order is a state collapse, triggered when the network encounters the physical resistance of the space hosting it. If this hypothesis holds, we can calculate discrete mathematical bounds by identifying the universal geometric constants that govern the manifold itself. We begin by viewing the empty spatial manifold as a tensioned field, the vacuum environment that hosting the network. Adding individual vertices into this system introduces what we define as raw informational mass. This mass carries internal topological pressure and entropy, which we can map through a modified Gibbs potential. As mass enters the system, the internal pressure on the manifold rises. Each newly added vertex acts like a microscopic clock in a quantum cavity, performing a partial measurement on the color state of the manifold. The cumulative effect of these measurements triggers the quantum Zeno effect. The spatial manifold itself inhibits the chaotic expansion of the graph's mixed state through constant interaction. When topological pressure reaches a critical limit, the system avoids a vacuum force divergence by forcing the network's color state to resolve into a definite structure. This tension is defined by irrational spines, constants like pi and e, that physically govern the growth and closure of geometry within the manifold. Within this continuous space, the golden ratio, phi, represents the absolute limit for recursive packing efficiency. By combining these constants, we find the rate of descent, pi times e divided by phi. This is the geometric equivalent of gravitational acceleration. This curvature comb chart tracks the structural tension as the graph's mass interacts with these irrational spines. This local minimum, the valley of alignment, is the exact coordinate where spatial resistance forces chaos to crystallize into order. Applying this framework to Theorem 1 provides a mechanical proof for the diagonal Ramsey number bound. We view the growing graph as the one skeleton of an n-dimensional simplex. As vertices are added, the geometric volume of mixed red and blue edge partitions grows exponentially. The critical moment occurs when the informational mass exceeds the continuous packing density limit of phi. At this point, the internal pressure of the mixed bonds violates the structural stability constraints of the hosting spatial manifold. The system responds with a localized, violent expulsion of all mixed color bonds. This is the same mechanical process seen in fluid dynamics when a gas instantly condenses into a solid under pressure. The monochromatic subsimplex emerges as an unavoidable structural condensation, a geometric requirement to maintain the integrity of the manifold, regardless of the coloring strategy used. We see the same physics at play in Erdős-Rényi graphs, specifically inside that critical window where edge probability equals 1 over n. To minimize entropy while growing, the network forms acyclic fractal trees. This rapid outward branching is a non-solenoidal flow, adding mass directly into the solid fluid interface of the surrounding manifold. This follows the aeronautical vortex ring state, where a system's growth rate outpaces the capacity of its environment. The network's descent rate eventually equals the downwash velocity of the spatial volume. This creates an insurmountable spatial drag, defining the n to the 2/3 scaling limit. Fractal expansion ceases, and the structure is mathematically forced to fold back onto itself. This folding mechanism initiates the rapid formation of cyclic bonds, instantly spawning the giant component. Bringing these two disparate mathematical mysteries side by side reveals their shared structural boundaries. The golden ratio acts as the absolute packing boundary in both formulas. The rate of descent operates as the universal spatial resistance constant for both. The threshold mechanism remains identical, whether the system is crystallizing a monochromatic clique or condensing a giant random network. The era of mapping these phenomena through probability provided only loose approximations of these thresholds. Extremal combinatorics has evolved from probabilistic mapping into the rigorous study of high-dimensional thermodynamics. As we model networks scaling toward infinity, the algorithmic search for statistical likelihoods becomes unnecessary. The emergence of absolute mathematical order represents the unavoidable mechanical destiny of a saturated spatial vacuum.